Hi guys, and welcome to AtCoder Beginner Contest 252. So this time I was able to solve problems A through G in contest, and later I solved problem H, but it was a little bit too hard for me to solve in contest. And because of that, I wanted to ask you, before we begin, whether or not did you know about meet in the middle technique? So yeah, that's gonna be the question for today. Let me know in the comment section down below, because I kind of knew it, but at the same time, for some reason, I completely haven't thought of it in contest. So yeah, it just, for me, just something weird that appears every once in a while, and I forget about it before it appears next time. So let's jump into the problems now. Problem A, ASCII code. You were given literally the code of the letter and you were asked to print the actual letter. So my submission for that problem would be, let's just read an integer and print it as a character. That kind of works this way in C++. As you can see, it took me 30 seconds to code, so yeah, that kind of makes sense. In problem B, we had n types of food. Each food had some tastiness, and we also had some dislikes for food. We took a random food with greatest tastiness, and we needed to check if there is a possibility that we dislike this food. So for this problem, I first find maximum tastiness, and then I just check if any index in B, the corresponding value is equal to maximum. This is a strange way of writing it. If you're not familiar with STL, you can just write a for loop instead, but yeah, I wanted to check if I still remember how to do it. So in problem C, slot strategy, we had slot machine. So it had like several wheels, n wheels. Each wheel contained all digits from 0 to 9 in some order. And like each second they spin by one position, they rotate one to the left, or to the right actually, to the left. And you want to align them, so like at any second you can stop at most one wheel, so this gets fixed. You wanted to align first characters. So it actually took me a while to understand how this works, like 5 minutes is a while. So my solution for that would be, let's loop over something that is small in the problem, namely over the set of like possible strategies. That is, what digit do I expect to see on first position? Like, let's say I want to not only win, but also align all digits 1, right? And how long will it take me? Well, clearly it depends on how many times each how many times digit occurs in each position, which I define with remainder. So if you calculate how many times each remainder each position has given value, has given digit, then your positions are kind of independent, because if you have multiple wheels, like one wheel, you need to stop it 3 seconds after the process begins, or like 13 or 23. This is clearly independent for like 7, 17, 27, 37, etc. So the time you need would be like whatever remainder takes longest among the 10 of them, and one remainder takes that long to stop. because first one you stop on j and then you add plus 10. So this way you get your time to win for a given digit, and then obviously you can pick whatever digit yields the smallest result. Then I skipped a problem, but I won't skip it in the editorial, because my idea for problem D was very bad. Like in contest I did something very bad. We are not going to go over that submission, we are going to consider what I did after the contest. So here we had an array, and we needed to count number of ordered triples such that 3 numbers are distinct. So oftentimes when you need to count triples, you may fix something, generally speaking the middle, and then consider how many other elements you can add to middle. So what I say is that choosing 3 different elements, let's fix whatever element is going to be middle by value, not by index but by value. So you can compute frequency map. Then you can record frequencies in this order. Iterating over C++ map gives the sorted order of keys, which is exactly what you want. So clearly the answer of the problem can be determined just from this array, of like frequency array in given order. Then if you consider any middle element, there are several ways to choose it. Then we need to choose one greater element and one smaller. Greater and smaller can be pre-computed in linear time. So that is just what you expect it to do. In contest I did some inclusion-exclusion, if anyone is interested in that. In problem E, rod reduction, we had some graph. We wanted to select only some tree, spanning tree, such that it minimizes the sum of distances. So for this problem I noticed that like minimizing sum of distances is kind of a weak constraint. In fact, we can select a way in such a tree in such a way that minimizes all individual distances. And this is well known. This is just what Dijkstra does, right? Dijkstra computes shortest distance for every vertex. So I started implementing that. Here your standard Dijkstra goes. But then you also understand, like, wait a second, I actually need to select some proper tree and not just say like what is going to be the sum of that value of distances. So here I come up with the following observation, which kind of can be seen as a definition of the extra tree, is that if for every vertex B there clearly exists an edge from A to B with length C, such that the shortest distance to B is equal to shortest distance to A plus C. That is pretty much the definition of shortest distance, that there exists such an edge. And if we choose one incoming edge per vertex, then we automatically get spanning tree. It's not hard to see. Right, like each vertex has exactly one incoming edge, then you get a tree. So yeah, we can just print this tree. That's roughly it. Yeah, and I skipped problem D in contest because this appeared to be like very obvious to me. Then I also skipped F, but actually F is a nice problem, so we are going to take a look at F first. So in problem F, we have a loaf of bread of given length. We want to partition it into pieces A1, A2, and AN, and then we may have some leftover. As you can see, sum of AI's is less than or equal to L, and not necessarily equal. And when we partition loaf of length K into X and K minus X, so we need to partition. For this we can apply sequential cuts. Cut costs however long was the original bread, loaf. So yeah, and we need to minimize cost. So for this, I noticed that if you consider a binary tree that arises from this process, so like originally, let's create one vertex to represent the entire loaf of bread. Then you split it into two halves, then you split one of the halves into two again, etc. Then every segment will be counted, like each leaf of this tree corresponds to some individual segment, let's say A2. And A2 will be counted in price, in cost, as many times as deep AI is. Because it gets counted once per layer. So then we get some like well-known problem that I realized at some point that it is well known. This reduces to just Huffman coding, which is non-mathematical construction to yield optimal construction for exactly this problem when the cost of each vertex is the depth. So yeah, the optimal strategy is to always merge two smallest intervals together and create one vertex on top of them and continue your process. So yeah, you just create a multi-set of integers. If you have any left over, you must include it as an individual piece. It's not hard to show that it's always optimal to have leftover as one piece. And then you just repeatedly take two smallest intervals and merge them and put the resulting interval back. And that works. In case you don't know what Huffman coding is, now is a good time to learn. Next problem, G pre-order. I believe I have seen this problem somewhere some time ago. So that's why I skipped F, because like I always make sure that I read at least two problems. Well, after like obvious ones. Like if I cannot immediately solve problem as it was the case with D, then I read next problem. So I read F, couldn't solve it immediately, read J, was able to solve it, so went with it. Then problem J, we have some rooted tree with n vertices, labeled vertices. We record our pre-ordered traversal, but also our pre-ordered traversal satisfies the following property. Whenever we have several children of a given vertex, we always traverse the subtree of the smaller one first. But other than that, it's just a regular pre-order. And tree does not have to be binary, by the way. It just so happens that in this case, your tree cannot be non-binary. So we needed to count the number of ways to restore rooted trees from given pre-order modulo some prime. And n was very small, so I immediately noticed that it is likely to be interval dp, or range dp. So for every range in this pre-order, we want to count how many different trees can be formed from labels from that range. So yeah, and then for one you can afford off and time per one transition. But also I remembered some idea about counting trees that I have seen before is that it's often useful. Like if you cannot count trees directly, then sometimes you will want to count forests, because essentially a tree is just a root and a bunch of forests. So that is a very common idea. I remember another problem on that, but it also required something with counting trees with given in-order traversal, I believe, or something like that. The difficulty of that problem was that you needed to somehow understand where the root could have been, and then do some work based on that. But in this problem, we just need to introduce like dp3 of I and j will be of L and R will be how many trees can you form from range from L to R, and dp forest will be how many forests you can form. Obviously, there are some initial conditions and final answer, but other than that, the more like dp trees is more or less boring. Like you know that in each range, first vertex needs to be the root. So dp of 3LR is essential dp forest left, skip the root and build yourself a forest, which is like core idea of why we even have two dps. You can, because of that, obviously, you can replace this with dp forest and this with another dp forest to only have dp of forests, but I find it clearer to express it in this way when you have like separate dps. And now how to count forests? Well, you need to like check what's gonna be my first tree in the forest. So you loop over all possible first trees and you check if next forest will satisfy whatever condition it must. In this particular problem, it needed to start with a bigger label than the first tree. Otherwise, they would have been visited in a different order. So yeah, but idea of counting how many forests satisfy some condition as a utility function essentially for counting trees is very important in my opinion. So yeah, let's have we solved problem G. Now problem H or X as they call it was way more complex. I don't know like if I could have figured it out without some help from the editorial. But anyway, in this problem we had some gemstones of different colors and beauties. So there were at most, like each color was from 1 to C. We wanted to construct a necklace by choosing C gemstones of different colors. And then the beauty of the necklace is the XOR of the gemstones beauties. After we did all this tedious work, we wanted to find the beautifulness of case, the case greatest beautifulness. So let's consider all possible ways to construct a necklace. Among each of them has some beautifulness, which is equal to XOR. And then among those numbers, we want to find case. So yeah, in contest, I just kind of assumed that it was too hard, which was not a smart thing to do. Obviously, I should have tried at least something, but yeah, I was being a bit lazy. So in this problem, because of how constraints are, like n is fairly small and c is fairly small, you may start thinking, how many different necklaces there are? Like if we need to find case, maybe we need to just like learn how to count the number of necklaces. You will soon realize that if you compute a frequency map of colors, the number of necklaces is just the product of values in this frequency map. So you have several numbers with some at most 70, and you are interested in maximizing their product. Well, after some manipulations, like let's say, what are the possible ways? Let's say I have 35 elements, 35 colors, each appears 2 times. So you get 2 to the 35th, which is a lot, but like not infinite number, which is like 2 to the 35th is way smaller than 10 to the 18th, because it's like 2 to the 60th. So that must have gotten me started on the following idea. Fortunately, it didn't, but the idea was like, so roughly, let's say 10 to the 12th. Let's say 10 to the 12th is how many possible necklaces there are. Well, 10 to the 12th is an interesting number. It's roughly 1 million squared, and 1 million is kind of small. So we may apply meet in the middle in the following way. Let's consider all colors, all C colors, and partition them into two groups such that products are roughly equal, and roughly equal to 1 million. Now we need some meet in the middle. How do we do it? And also we need to find case. So finding case sounds like binary search. Let's try some given XOR and check if it's true that at least k pairs have greater XOR. So obviously, like for each, as I said, we partitioned colors, right? So for each combination within one part of the partition, you can explicitly generate them. There are not that many, at most 1 million. So you know bitwise XOR of each combination within each part. After this point, colors become irrelevant. The only thing you need is like you have 1 million numbers, another million numbers. You can combine any pair with XOR, and you want to count what will be the case largest result. So this is clearly binary search. Like let's take any fixed target value and count whether or not there are at least k pairs with greater XOR. How to do it? Well, for each value in left part, you can count how many values in right part give big XOR by performing something like binary search on a bit try, or not binary search, just descent on the bit try, right? Like you put all elements of the second group of colors into bit try, and for each element of the left part, you descend in binary try and then check. Unfortunately, that is a bit slow. So what you can do is maintain those partitions a bit more explicitly. And do not like perform entire descent like at one moment. Let's see what I mean. So first I partition, that is not very interesting. So I obtained some partition. After this I perform this kind of binary search where I try to individually turn bits on from most significant to least significant. So what happens is that I have some partition already. Now I want to partition them by current bit, each part. So that's just what I do. So I want to record what elements in left hand side have current bit set on and what elements have current bits turned off. Same for right hand side. So now if I want XOR of 1 in the current bit, then I need to combine 0 with 1 or 1 with 0. Makes a lot of sense. If after combining all of that, I got enough, like at least k, then I now know that it's possible, like k's largest pair will have this bit turned on, because there are at least k pairs that have this bit turned on. And this is the most significant bit that we haven't considered so far. So in this case, I will continue my search among only the pairs 0, 1 and 1, 0. And these pairs, like, they don't need to overlap in any way. So I will only consider pairs 0, 1 and 1, 0 separately. This could have been written as a recursive function. But I believe that this way works a bit faster. Like if you don't need to copy partitions all the time. Although I'm not sure that there's no copy. There probably is, right? It's not in place. Anyway. Like, we may have multiple partitions to go through. This is the main idea. At this point, we know how to separate them. That we only want zeros with ones and ones with zeros. This reduces the search space for the next step. However, if I haven't gotten enough pairs, then current bit is impossible to turn on. Or rather, case largest will have this bit turned off. So I record all pairs who have it turned on, and then I will only consider pairs 0, 0 and 1, 1. So this is like iterative descent on a trie, but we perform descent for all numbers by 1 bit. Instead of for each number individually traverse the entire path. So this reduces complexity from log squared with one log coming of binary search and another log coming from descent, because now per one iteration of binary search only one iteration of descent happens, only one partition happens. So overall complexity becomes log maximum value times 10 to the 6, where 10 to the 6 is like roughly the size of one part of the original mid partition. So yeah, actually a hard part here was showing that 10 to the 6 is indeed the size, so like bounding total number of combinations of necklaces. I couldn't do it in contest, and like I had to consult Editorial to understand why this happens. And I think this has been the case with many recent ABC H problems. Like you need to a certain extent, you need to believe in yourself. I believe that this number will be small, and then you can keep thinking and eventually invent this standard parallel, let's say parallel binary search. I guess this, you can call it parallel binary search. So yeah, it was the case with many recent ABC H problems. Like you need to believe that something will work fast. I don't know. I'm not a big fan of it, but it's useful to know nonetheless. So yeah, that was the contest for you. Thanks for watching, and I'll see you tomorrow with Codeforce's Div 2 round, I believe. Bye bye, guys.